Yeah.
Oh, wow.
I got it last time when we were together in that class.
Oh, no, still looks good. I buy my mom one. I need to buy myself one. But I'm not rich enough to afford
But
it.
how are you gonna be part with your face? You can't.
I can't. You're right.
All the things I have done to you, you're gonna just still over like this. You're looking forward to it.
Oh, those photos. It's not even enough storage on there. 16 gigabytes. How much is yours? 64?
I think so. I don't remember. And not like I do a lot
Let
of
me
things.
do a swatch test of all these colors. That was black.
Well, it says
Wait,
I'm pure.
I should write black on it. Alright. This is blue.
So then see what
Okay. This is red. And this is purple. Oh wow, I do like the way it writes. It's very nice.
needle.
I'm ready when you're ready. So your test is normally what day?
Monday.
Says on Monday.
Normally it's on Monday. I'm gonna push it to Wednesday. But what really frustrates me is you don't listen, and then I feel really upset when I start grading the test and I feel like they didn't do what they're asked to do. Believe me, if you do what I asked you to do, you will do fine. Now, you don't jump straight to the pre-test, please. Jumping straight to the pre-test is not studying, it's trying to answer questions without even, you don't study while you're answering questions. You first study, then you try answer questions. And you might think, you know what, you don't have time. Well, too bad. This is the class where you have to put a lot of time. So how do you study? How do you study? And I can't say it enough, I can't say it enough for this course. How do you study for this course? Read the book first. Read the book. You have to read the book. If you're not going to read the book, you're not going to learn the right way to study. Real learners are people who read books. And I don't know if I told you this, when my son went to Hopkins, they used this book. Before he even showed up, they told them in the summer to study all the chapters, do all the problems, and then show up. So this is what you're competing with, and I'm not kidding you. This is the same with other people. They don't even teach, and it's a lot of money, but think about it. They tell them, they pick this particular book, and they say, you do these first 12 chapters, and you show up the first day of class after you studied all of them. So what does it mean? It really, you can't learn without reading the book, reading your notes, and then do the questions in the text. And you might say it's too much work. Well, if you finish at least all the questions in the text, you're in good shape. But if you try to do the pre-test without reading the book, you're in a very bad shape. So you have to decide. Would I rather invest time doing the problems in the text and get something out of it, or just go straight to the pre-test and then end up with failing? And I tell you, because I've been teaching this course, and I saw those who follow, those who were on track, they always end up with an A from day one. They listen, and they read, and they sit, and they assign time, and they do it. It's not impossible. I know you can do it, otherwise I wouldn't even waste my time. I know you can. Every single one of you can. But if you just listen, because I've been teaching since 1981. Think about that, okay? I know what I'm talking about. This is not new for me. And you can't take shortcuts no matter what. So my plan is today to finish 18 and 19, and it's very possible. And also, I've always said, pay attention, don't take notes. Read the book, pay attention to what I say. Video record it, it's okay, but don't waste time writing, because I tell you one thing, the brain, I read so many books about how you learn. I don't care how smart you are, the brain Even if you can multitask, you can't write while understanding. You either focus or write. Doing both is not going to be easy, and it's not going to be efficient. That's all I can say. So pay attention and don't talk. Also, if you have a question, please ask. It's already hard to focus on this stuff. There's so many little details that matter. So I hope I said it, and I'm not going to say this speech again. I'm done from now until all the next future chapters. So hopefully you listen and you really appreciate this, because I'm telling you, because I know what it takes. And you know, you have every day spend 3 hours. And I'm not exaggerating when I say 3 hours. 3 hours, that's what you do. Now, how do we read the book? It's not a novel. You know, I read a novel, I can read it in 3 days. It's easy, you agree? I mean, I can really read, like, turn pages. This weekend I read 2 books, you know? But this book is different. So how do you read it? Change the title and subtitle into questions before you even start reading it, okay? Let's say now I'm on chapter 18:12. It says the effect of substituent on reactivity. This is section 12, okay? I'm gonna change it, before I even start reading, I'm gonna change this title into a question. When it says the effect of substituent on reactivity, immediately I'm asking myself, what are the effects? How do they affect? And you can think of any kind of question. When you write it down, I tell you what happens in your brain. In your brain, you're already opening a box to put that information when you start with a question. But if you read in a linear way, your brain is going to take it, put it in the short-term memory, and dump it later. Whereas if you start with the question, it knows exactly where to put it, and you will remember it. And I'm telling you, because I've been reading tons of books about neuroscience and how we learn. Prepare the boxes for the information to be in, and the best boxes is through questions. So what are the effects? How many of them? How do they affect it? And as you write these questions on the margin, you read and answer. Every time I read a little bit, I answer. Wait a minute, how many of them did they mention here? Let me see. How do they do it? Let me see. So that's how you study. That's really how you study. You know, when you go to these colleges, that very expensive one, Cornell and Hopkins and Princeton and Stanford, they make them learn how to study before they even take any class. They say, you need to read the book, you need to know how to read your book, you need to know how to take notes before you even show up. So you're supposed to even do this before you even see me, before I even start talking about the book. So please don't forget that, okay? Now, one last thing in chapter 18, and we'll be done with it, which is, we said that benzene is nucleophilic, you agree? So all the reactions on benzene are what? Electrophilic, so we have to bring something positive. But then there is a section in the book that says nucleophilic aromatic substitution. So it means that there are reactions that are nucleophilic on the ring. So when does that happen? First of all, the benzene ring by itself is nucleophilic no matter what. So there's no way you can add a nucleophile here. But when does this become interesting? If you have a withdrawing substituent, what is the withdrawing substituent doing? It's pulling the electron, so it's making the ring less what? Negative. So you have to have electron withdrawing substituent. If you see NO2, 1 or 2 or 3, the more NO2s, the more electrophilic it becomes, okay? And then you see a substituent that can be replaced. So you have to have electron withdrawing. I'm giving you the hints because the reaction, when you answer it, it says what are the product. It's not going to tell you, hey, look at me. You know, you need to look at it. So you have to have an electron withdrawing substituent, and you have to have a leaving group. So halogens are good leaving groups. So this is a leaving group. So if you have these two conditions, you have something that pulls the electrons to make the benzene ring more positive, less negative, I should say, and you have a good leaving group, then you can substitute it, okay? So what is being substituted? Here's an example. If I bring here OH minus, this is a nucleophile, you agree? The only place it can't attach to the ring, you already know anything that attached to the ring must be positive. But if I bring an OH minus and I have a good leaving group, what's going to happen is we're going to have a nucleophilic substitution. Okay? So here, the first step, you can bring OH minus, but then you really have to heat it. You really have to shake this thing. So usually it's a high temperature. So it says OH minus at 160 degrees, which shows that it's not easy, but it can happen, okay? And then the second step, you protonate. Yes. So what you end up with is the chloride would be substituted with an OH. Okay, plus HCl. So you don't need to write the mechanism, but you need to understand that it can happen. Nucleophilic substitution can happen. Another one is this. If I have two nitrites, so I have a chlorine here, I have an NO2 here, and an NO2 here, what do you think is going to happen if I use the same reaction? Which one will go faster? The top or the bottom?
Bottom.
The bottom, why? Because you have two electrons withdrawing. So the more of this you put, the higher the chance of it to happen. Okay? So same thing, same conditions, you're going to end up with OH. So normally benzene can only undergo what? Electrophilic substitution. But substituted benzene can undergo nucleophilic substitution. But it has to be substituted with what? Two conditions. You have to have what? Electron withdrawing and a good leaving. What's the job of the electron withdrawing? What is it doing?
Making the ring more positive.
Making it less negative. And the good leaving group allows you to do the substitution. Yes.
If the leaving group is on the meta position, does that?
Doesn't matter. Good question. It doesn't matter which position they are. The only condition is you have two substituent, one withdrawing and one a good leaving. Okay? So is everybody clear? So benzene normally only react with electrophiles, but substituted benzene can react with nucleophiles if you have these two conditions. So that's the last part of the chapter. Any questions? So we're done with chapter 18. Okay? Yes.
What happens to the NO2?
Stays there, doesn't touch, it's not touched.
Oh, okay.
It's not a good leaving group, so I just didn't finish writing it, but it's still there. Yeah. Yeah. Yeah, sorry, it was me moving too fast. Yeah, good question. Okay, so now we're moving to chapter 19. Now, why do we study these two together? It's because they have a lot in common. They're both about aromatic compounds, okay? So chapter 18 and 19 talk about aromatic compounds. And of course, 19 has the amines, but the amine is the least studied functional group because amines are literally nucleophiles or bases. So you're going to just look at them as nucleophiles and bases. And as we go through other chapters, we will see how they are used. So I'm not going to waste time here for amines because they're really something that is just a nucleophile. So I know it's a nucleophile, so I'm just going to, whenever I need a nucleophile, I can use an amine. And whenever I need a base, a mild base, I can also use an amine. So what else then in chapter 19 are the other aromatic compounds that are called heterocyclic. So what does it mean, heterocyclic? It means in the ring, you don't have just carbon. You can have a different atom. So homocyclic means all the atoms are the same. Heterocyclic means one or two of the atoms are not carbon, or even three. So you have a mixture of other atoms. Now, we're not going to study all of them. We have 5 of them or 4. I don't remember. So I'm going to write for you some heterocyclic compound that appear on chapter 19. Here we go. As I said, even though chapter 19 talks about amines, just look at them as nucleophiles. So don't worry about that for now. Just anything negative that wants to attach. So what are the aromatic heterocyclic compound in this chapter? There are 4 of them. So the first one is this, which you already saw before. What is this called again? Pyridine. Then you have these 5 atom rings. Okay, and then the last one, actually I'm going to put the N here, the O here, and the S. So the name of these compounds, this one is pyrrole. Sorry, this has an H. So this is pyrrole. The other one, pyrrole, is 2 R's. This one is purine. This is thiophene. And of course, this is purine. Okay, so these are the 4 compounds that are studied in this chapter. So the question is, why are they in the same chapter? And the question is, how are they similar? How are they different? As usual, every time you're going to study compounds, always focus on how are they similar, how are they different. So one first thing you observe is this is 6 atom ring, and these are 5. Okay, that's one thing. What else can be observed here? Do you agree that they're all aromatic? Because they all have 3 pairs of electrons. So what's the difference between pyridine and the others? There's some major difference here. I'm not counting how many atoms. They both have 3 pairs anyway. The lone pair here is outside the ring. And here, the lone pairs are part of the conjugation. Okay, so that makes a huge difference. So for pyridine, the lone pair is not part of aromaticity. That lone pair would be like a base. It has nothing to do with the ring. It's like a different creature on the outside. But the others, the lone pair is part of the conjugated system. Okay? So that's one thing. Now, so as you can see, we can write resonance forms. So I can move this pair where? Left or right? If I move it here, what do I need to do with this? Put it on this carbon. Then I can move it back here and this here. And then back again, this here and this to the, do you see? So your resonance form, meaning the lone pairs there are part of the conjugated system. The lone pair here is outside. Now, which one has more electrons per se? When a ring has 2 electrons completely devoted to the ring, it's different than pi bonds. You agree? Pi bond is 1 electron from each atom. The lone pairs, the 2 electrons are added to the ring. So these have higher electron density. Okay? So the last three there, it's almost like they have, although they seem to be like 6 electrons, but they have higher electron density. Why? You can see it with the number. The pyridine has 3 pairs distributed in how many atoms altogether? 6. And on these 3, you have what? 3 pairs distributed on how many atoms? 5. Okay, so they're more dense in terms of electron, which means what? Are they more nucleophilic or less nucleophilic?
Yes.
More nucleophilic than what? Than benzene. Okay, so these three, they have 3 pairs of electrons distributed in 5 atoms. Benzene has 3 pairs distributed in 6 atoms. So we already know benzene is nucleophilic. You agree? How about these? These are more nucleophilic. Is everybody understanding why? So these 3 are more nucleophilic. Okay? Then what? Then, of course, then benzene. So they're all more nucleophilic than benzene. Why? They have a higher electron density. So what does that mean? Are they more reactive or less reactive than benzene? More reactive. So which means that the reactions we saw in benzene will also happen in these compounds. Okay? So reactions that are observed in benzene will happen on these, and they will happen faster and better. They don't need too much strength to push them. And what are the reactions again? What are they called, the reactions on benzene? Electrophilic substitution. So all of these will undergo electrophilic. Which include what? As a subcategory, as electrophilic substitution, what are the reactions? Halogenation. So here you say halogenation, nitration. What else? Sulfonation.
Alkylation. Friedel-Crafts.
And then Friedel-Crafts, which includes, of course, alkylation and
Alkylation.
So you start to see that if we study benzene, we already studied these. These will have milder conditions. So what does it mean, milder conditions? For benzene, we use, let's say, for halogenation, we use iron bromide. If I'm going to do bromination, I can expect to use a milder catalyst. I don't need too strong of a catalyst. So we'll see just the difference between benzene and these. But all these reactions will happen just like they happen on benzene. So that's why I say we can finish this chapter quickly, because the mechanism is the same, everything is the same. Now, how about pyridine? Is this more nucleophilic or less nucleophilic than benzene?
Less.
Why?
Because nitrogen versus carbon.
Well, we have still how many? The electron density is the same, you agree?
Yes.
3 pairs for 6 atoms. So in terms of electron density, they seem to be the same. But what's left for us to compare? The only difference is this has a nitrogen and this has a carbon. So to answer that, what do? If I ask you, how are they similar, how are they different? You're going to say, of course, one has nitrogen instead of carbon. So what does nitrogen has that's different from carbon? Why? It is smaller. So nitrogen is smaller than carbon. And what does it mean? Smaller? It means the electrons are close to the nucleus. So what are they going to do? The nucleus is going to pull. So here, the nitrogen, and is everybody understanding? The only difference is the nitrogen. The nitrogen being smaller, what is it going to do? It's going to have an electron withdrawing effect. You understand? It pulls because it is smaller. But is it by resonance or by what? By induction. It's called induction. Okay? So nitrogen is pulling on the electrons. So what is it happening? Then what's happening to pyridine compared to benzene? Which one is more electrophilic or nucleophilic? Benzene is more nucleophilic than pyridine. So which one then is more reactive? Benzene or pyridine? Benzene. So benzene is more reactive than pyridine because pyridine has an electron withdrawing atom. So are we going to have the same reactions as benzene? What is it going to happen? Maybe, but we need what?
A stronger catalyst.
Stronger catalyst. Okay, harsher conditions. So here, everybody understand that these are more nucleophilic, which means more reactive. More reactive than benzene. But this one, pyridine, is less nucleophilic, which is also less reactive than benzene. But in what way it's less reactive than benzene? In electrophilic substitutions. Okay, so we're comparing just electrophilic substitution. So I want to organize them then in order. I already know these are the most reactive. This is the least reactive. Benzene is kind of in the middle. But out of these three, which of these three is the most reactive? So what makes any one of them more reactive?
Pyrrole. Pyrrole is the most, and purine and dio.
Why? What makes them more reactive?
Similar to before, it's the size and electronegativity of the different atoms, the nitrogen, oxygen, and sulfur.
Did I ever use electronegativity? I hate that word.
Size.
I don't use electronegativity. I don't know if you noticed that. Did you notice this? I rarely use the term electronegative because it's almost like an old thing. It's all about size. So if you compare now nitrogen to oxygen, let's just compare nitrogen and oxygen before we even get to sulfur. What's the difference between nitrogen and oxygen?
Oxygen is smaller than nitrogen.
So what does, if oxygen is smaller, what is it going to do?
The electrons are closer to the nucleus.
It's going to hold on. So will it allow these electrons to move around? So this is less nucleophilic than that. Okay? So pyrrole is more nucleophilic than oxygen because the oxygen is holding the electron. It's not going to let them move around. So it's not going to make it more reactive. So this more reactive than this. Now how about oxygen and sulfur?
Sulfur is a larger atom.
It's larger. So what is a larger atom going to do?
The electrons are further from the nucleus, so they don't hold as tight.
So it's more spreading, which means it's going to give more its electrons. But, and this is what I mentioned last time with the halogen, these electrons are 3p. You agree? And these electrons are what? 2p. So are you going to have an easy transfer? No. So that's another thing that you have to think of. It's not only the size, it's also when you have conjugated system, is what orbitals are involved in the resonance. Okay? So sulfur, although it's bigger, you might say, oh, it's not holding the electrons, so it should be more reactive. You agree? You might think, oh, sulfur, the thiophene is more reactive because it's a big atom, it's going to let them go. But the problem is the conjugation system is not perfect because you go from 3p to 2p. So that makes the product different, makes the reactivity different. So then how are they in terms of reactivity? This is more reactive than this, and this is more reactive than this. Now, then where does pyridine falls? Pyridine comes right here. It's the least reactive of all, so it's after benzene. So the last one would be pyridine. Okay? So we're going to just leave this part like this. So in terms of comparison, pyrrole more reactive than furan, furan more reactive than thiophene, then benzene, then pyridine. So what does it mean? It means for pyridine, if we're going to do any electrophilic substitution, they're going to be very what? Hard. Okay, so here, very difficult to do electrophilic substitution. Here it's very easy. Okay, so pyrrole will react the fastest, the easiest in electrophilic substitution. And pyridine will react the slowest and needs a lot of hard work to push it. So you need very strong catalysts. So pyridine will undergo halogenation, but of course it's going to be very different from that. It will also undergo nitration. It will also undergo sulfonation, but no Friedel-Crafts. So you can do Friedel-Crafts on pyridine. Friedel-Crafts is already hard on benzene. It's going to be impossible on pyridine. So if we have to write the mechanism, we already learned all of that. So now what is the last question we can ask? I hope everybody understands how they're stronger than others, and read the book again, it explains it. Now read the notes, put it on the notes, it's written in the book. You have to understand before you do anything, okay? So what is our question then? When we studied benzene and we did all of this, if it's only one time, you understand, only attach in one position. But in this particular case, where is the halogenation going to happen? It's going to happen here or here. Do you see what I mean? So that's the last thing that's different. So we know that all of these will happen, but the question is, what position? Is everybody understanding what I mean? Because now we have a different atom. Is it going to happen on this atom? No, absolutely not. It's going to happen on the other atoms. So this particular atom right here is 2, position 2. We call it position 2. 2 compared to the hetero atom. So so this is 1, this is 2. And this is 3. Okay? So the question is, what position? Is it on C2 or on C? Are you understanding me? In here, how many positions we have? We have 2, 3, and 4. Same thing. Is it C2? Is it C3? is it CO4? So let's review one more time. All of these, as I rewrote pyridine, will undergo electrophilic substitution. But from pyrrole to pyridine, the reactivity what? Decreases, which means we're gonna need what?
Stronger catalyst.
That's what you need to write. You need to use different catalysts. So the catalyst that works for this might be different from this, and of course, then the benzene, then the pyridine. So the only difference is the catalyst and the temperature. Okay? For benzene, we know the catalyst. So now we know what are the catalysts that are used for the others. They're definitely different. Okay? The other question is, okay, we know the catalyst is different, then where? So that's the new thing. That's the only new thing in this chapter, is to understand how are they similar, how are they different, and what is the position where these reactions happen. Okay? So if you understand that part, you're good to go for the rest of the chapter. So let's show how this works. Okay? I'm going to start with, I'm going to leave pyridine last, even though my notes start with pyridine first. And it really doesn't matter because, so let's try pyrrole, okay? So, for example, I'm going to just show you in comparison these, what type of catalyst they use. Okay, just quickly, before we go to what position. So it shows, the book shows you that if you take benzene and you want to do a halogenation, we already, or Friedel-Crafts. So this is an acylation. What was the catalyst for benzene? Do you remember? Very good. And you end up with the substituted benzene. Okay, and of course, first step is aluminum chloride, second step is lots of water to get it out, the complex, remember? And of course, it gives you HCl. Now, if we use the least reactive, so I start with this, so we go to thiophene, okay? So thiophene here, same thing, Friedel-Crafts. So I'm still gonna need a catalyst, but it doesn't have to be as strong as aluminum chloride. So guess what they use? They use tin chloride. Okay, so tin, see here, aluminum, tin is pretty cheap and it's a 4+. Okay, so tin chloride would be sufficient. So same thing, first step is tin chloride, second step is water. Then you end up with your Friedel-Crafts. And we still don't know which position, so I'm just going to throw it in here. We'll talk about the position thing. Okay? Of course, plus HCl. Now we go to pyrrole, furan, I'm sorry. Furan is more reactive than thiophene. So here all you need is boron. Boron is smaller. So Lewis acid, they're all Lewis acid by the way. So this would be BCl, BF3 here, they use F. And THF, which is and non-polar. We'll talk about these solvents, and then water. So you will end up with the furan. And then the last one, which is pyrrole. And you heard pyrrole reminds you of what? Any word you heard in everyday life?
Would Theosphere have a methyl group instead of the chlorine?
Sorry, yeah, it should be mental. I'm sorry. Thank you. So pyrrole, you heard about pyrolytic compound, pyrolytic, like for explosions and fireworks. There's a word there that says pyro something. Pyro means explosion, and it's because they're very reactive. So pyrrole is extremely reactive, and in this case, actually, we have all we need. It can react with an anhydride, so we don't even need to use acyl chloride, and you don't need any catalyst. Just put them together, and what you end up with is okay. So you start to see the difference. This is stronger than this. This is stronger than this, and here there's absolutely no catalyst. It happens without any catalyst. Yes.
For the furan, is there nothing in the second position?
The second is water. I mean, my brain is moving faster than my writing. Or my writing is not in phase with my brain. Yeah.
Do we have any other products from the
Yeah, it's still it's complicated, so you don't have to worry about it. Okay, so this is still to talk about what nucleophilic substitution and to talk about how they require milder conditions. Now, what is the position? So that's where we want to explain. What position do they attach? So, oh, where did I put my stuff? I guess I skipped. Yes, here we go. So let's look at I guess I shouldn't have skipped that part. But, they always attach at the C2. But so in here, for all of these, they do it at C2 first. But if C2 is taken, they go to C3. So first choice is C2. But if the position is taken, they go to C3, which means it goes both, but C2 is the preferred position. Okay? So all of these compounds, the very reactive ones, will undergo electrophilic substitution, and it will happen at C2. And if you have no spot, if all the C2 positions are taken, it will go to C3. Okay? That's all you need to know. But now let's go to pyridine. Pyridine is a different story. Okay? Because we already said pyridine is not reactive. So let's look at pyridine. If I have N So let's say I have my electrophile, which is Y plus. Remember, it's electrophilic substitution. So here we have an H, and I have Y plus. So what can happen is this opens. So if it opens, you end up with H and Y. Now the nitrogen lost an electron. So the charge here is plus. You understand? So this pi bond went to the Y, and then it's plus. So what are the resonance forms here? You can move this here.
Bless you.
So now the N is fine. So H and Y. Now this is positive. Are you following me? Then this moves here. And then the last one would be what? Basically, that's pretty much it. Now you remove the Y and you make a double bond. So you have these three resonance forms if we attack the 2 position. Okay? Now let's see. So this is a C2. Now what if it's C3? So here you have the Y plus and the H. So now this opens. So this is C3. So what is the next step? This moves here. And then the next step Are we so far so good? Now let's try the C4. Okay, so I'm going to put it underneath it. So C4, meaning right here. Okay, so we have an H and I have a Y plus. Okay. So this opens, takes the Y, but it lands on the C4. So we have Y and H. And then this is plus. Then what's the resonance form? This moves here. Then the next resonance form, this moves here. Okay, So each one of them has 3 resonance forms. Now let's compare this to this. Look at where is the positive charge on the top one. Here it's on the carbon. Here it's also on a carbon. And here it's on the nitrogen. Let's look at this one. Carbon, nitrogen, carbon. So C2 and C4 are the same. They have the positive charge twice on the carbon, 1 time on the nitrogen. Now you look at C3. C3, the positive charge is always on the carbon. So the answer is, which one is better? Again, you see, if you have to explain things, you always have to do, how are they similar? How are they different? So what's best? To have a positive charge on the carbon or on the nitrogen? So before I even answer that, what do I need to look at? The size. So which one holds a positive charge better? Large atom or small atoms? Large atom, just like metals. Remember, metals are all large, so they are positive. So which one is larger, carbon or nitrogen? Carbon. So which one is better?
All 3 carbon.
So which position would be the favorite one? C3. So please write it down. C3 is the favorite position because the positive charge only lands on carbons, which are larger than nitrogen. So for pyridine, the reaction will happen only at what position? C3. For the other 3, where does the reaction happen? Preferably on C2, but it can go to C3. In here, it's only C2. That's the only position. Okay, yes?
Why is it numbered starting with this one?
That's how they number it. Yeah, they use 1 as the heteroatom, like nitrogen or oxygen or sulfur. Yeah, it's a little confusing, but that's how it is. Okay? So everybody's clear. So the 2 and 4 are not gonna happen, but the 3 will happen. Okay? So let's see some examples. We already said that for pyridine, are we going to have all of these? One second. Are we going to have all of these?
Except for the freedom.
We're going to have the first 3, but not 3 digraphs. And even if we have the first 3, what should happen here? We have to have a much stronger what? Catalyst. Yeah, what's your question?
Just like that pyro and grand stuff, where if C2 are both taken, we'll go on C3. Does it work like that?
No,
They just-
the only position is C3.
Oh.
This is very good question, actually. So for pyridine, only C3. If it's taken, no reaction. Okay? So let's see some examples. So of course, with pyridine, we expect that if for the halogenation we use iron bromide for benzene, we're going to still use iron bromide because we don't have a better metal. But what do you think will be different? But it's still going to stick to the same catalyst. What can I do to make it react faster? Higher temperature. So don't be surprised if you see similar catalyst. If it's the same, they have to push it harder with a different temperature. So here's an example. And I'm giving you all of these things that the book shows but doesn't say. Okay, the book shows you this thing, but doesn't explain it, because they assume you know that, you have different things to do when you want a reaction to work faster. Either change the temperature or change the catalyst. And that's from 201. That's why the book doesn't remind you these things. But since I know that you probably forgot, or maybe you didn't pay attention too much, or maybe you didn't make the correlation between the two, I'm here to say these things. So, and the book will use different metals, so don't be shocked if you see a different metal. If it's the same column, it means it's the same. The only difference is that ruthenium, for example, is much more expensive. So either you're going to go to ruthenium and you do it, and it would work beautifully. But if you don't have that much money, it's probably 5 times more expensive because it's rare. Then you just go with iron and increase the temperature, which is cost effective. So it's more about, not necessarily chemically speaking, but it's more about cost. So whenever you're going to see the catalyst, it's really like your car, in the old days, cars didn't have a catalytic converter in the exhaust. You all know that. The old cars, they just have an exhaust. Today, they put a little cylinder that has aluminum oxide or silicon oxide, depending on what the manufacturer put. And then they put platinum in it. That's why they're very expensive. That's why people steal this catalytic converter. So look at where platinum is. Nickel would have done a wonderful job, but it will require a much higher what? Heat. And if they heat it that much, the container will melt. So what did they have as a choice is to put platinum, but because it's very expensive, they have to know how to spread it out and use platinum, less of it, so that it's still efficient and make it work. So that's why catalytic converters in cars are very expensive. They're extremely expensive, and people steal them actually. They know if they're really into scrap metal, they will go and grab these things in any car that's been, broken or thrown away, or sometimes just parked in front of your house. They will take it out because it has platinum. Yeah. So I'm just giving you all these ideas. So when you see all these metals, always look at the periodic table. Nickel is the cheapest, then palladium, then platinum, but they all have the same kind of chemical properties. So they all will do the same job, except that one is more efficient. So here, pyridine, we have it with bromination. So if you're going to use FeBr3, the temperature here must be 300 degrees Celsius, nothing less than 300. And where is the bromine going to land? In what position again? So it has to be, right? That's what you need to remember. I need a stronger catalyst, and I can only make it land on the 3rd position. Now, sulfonation, same thing. I want to sulfonate my pyridine. So we still use H2SO4. But here, of course, the catalyst is also H2SO4, but the temperature is 230, which is pretty high. And again, it will land on the C3, no matter what. So it's always going to be C3 position. Whether you put it to the left or to the right, it doesn't matter. It's a C3. Now, will it happen twice? Can you have double sulfonation? What does this do? Is it an electron donating or is it an electron withdrawing? So it's all about whether it's donating or withdrawing. If you have an electron donating, what happens? The reaction would be easier. But if you have an electron withdrawing, the reaction would be even harder. So if you do it again, where does it land? If it's an electron donating, where does the other land? the other C. So you can also do the same reaction twice if you have an electron donating substituent. So is bromine an electron donating? We did this last time, I'm not gonna reteach it. Which page you have to look at? Remember, there was a page with that big table that tells you activating, deactivating, that's what you need. Okay, is bromine activating or deactivating? Deactivating. So will the reaction go again?
No.
How about the sulfonation? SO3H, is it written there? Look at the table.
Deactivating.
Strongly.
Deactivating.
So is the reaction gonna go again?
No.
Okay? These are few things to remember, that's all. So for the nitration, very similar. So the nitration and the catalyst is sulfuric acid. And here it's 300 degrees Celsius. And can nitration undergo, again, is this an activating or deactivating? So it will stop there because it's already not very reactive. The only way is if you can change one of these into something that is activating for the reaction to go again. Okay, so, but something special about pyridine. So what did we say, pyridine? It only happens in C3 and no Friedel crafts, okay? No Friedel crafts. And it requires higher temperatures. I'm just kind of summarizing. Why? Because it's not what? Very reactive. So if it's not very reactive towards electrophilic substitution, pyridine will do nucleophilic substitution. Okay? So these here, they don't do nucleophilic. You understand? You can't bring a nucleophile to these. There's no way. Because they're very nucleophilic. Okay? You can't bring a nucleophile to these. Can I bring a nucleophile to benzene?
Yes.
Yes, only if it's what? Substituted and if it has what?
Good leaving group.
Good leaving group and electron withdrawing. So now let's look at pyridine. Pyridine being the least nucleophilic, it means we can do nucleophilic substitutions. Okay? So pyridine is different from them because it's not very nucleophilic, so you can do nucleophilic substitution. If I'm done with the chapter today, then what are we going to do until next week?
Lots of problems.
Yes. Okay, so let's try pyridine. Again, just like benzene, what did we need to do nucleophilic? It has to be a nucleophilic what? Substitution. You understand? You need to remove something and put something else. So for benzene, what needs to be removed to do nucleophilic substitution? Which is usually what? A good leaving group. So for pyridine, it's the same. Can I remove an H? Is H a good leaving group? So I need to have a substituent. So nucleophilic substitutions will happen on substituted aromatic compounds. Is everybody understanding what I mean by substituted? It means they have to have something on them to create that nucleophilic substitution. Whereas here, electrophilic substitution, they can be done on the bare substance. Doesn't have to have a substituent. Is everybody understanding? So a substituted aromatic compound means a compound that has a substituent already. So we're going to try with pyridine with the substituent. So here is pyridine. And I'm going to put a substituent here. Don't tell me how we can do that. That's the genius of some organic chemists. They know it only happens on what position? C3, but they know how to figure it out. That's engineering, where they engineer molecules. And I just read yesterday, like they just discovered a new antibiotic, which is a chiral compound. And because people can figure things out, but there's so many combinations. So now you have computer scientists and AI that is used. So the person who writes the codes, they write the code for the computer, and it tells the computer, okay, I'm going to give you all the tricks, then tell me how you're going to make this. And then it gives it back, and then the chemist will just double check if it's feasible or not. So now it's a combination of not only what is in the book, if you can code it and put it in the computer, then the computer can put so many things that our brain knows how to do, but it takes longer, but they know how to do it faster now. So that's called computational chemistry. So if you're a computational chemist, you're very good at coding, and you're also good at organic chem. So you have to be a genius. And of course, they get paid entry level 150 to 200,000 if they're very good at it. Yeah. Okay, so how does it work? So we have a substituted substance here. And then I want to bring a Y. The Y is negative. Okay? So it is a nucleophilic substitution, meaning one comes in, one goes out. But whatever comes in is a nucleophile, and whatever comes out is also a nucleophile. So how does it work? Well, first step, the good news about this is that we have a nitrogen. So what happened is this can come here, the nitrogen takes the pi bond. Okay? To allow that carbon to have 4 bonds, you have to remove 1. You agree? So it's always an addition followed by elimination. So there's no direct substitution. You have to add and remove. It's always add first, then remove. So what happened then is just like with benzene, it's the same thing. So we're going to end up with 2 bonds here, Z and Y, and now the nitrogen is negative and this. So step 1, you add the nucleophile and the pair moves to the nitrogen. Why? Because nitrogen is smaller than carbon, so what is it going to do? It pulls. So it allows that motion. Then the next step, now that we have this, the nitrogen gives back, now Z has to. So it's an addition, elimination, which is overall looks like a substitution. So this is the mechanism, okay? Now I put the Z here. The substituent is on the C2. I'm going to see what is my substituent on the C3 and what is it if it's on the C4. So let's put a substituent on C. So I have my Z here. Okay? Yes.
Does the substituent have to be an electron withdrawing substituent, or can
Yes,
it
it has to be a good leaving group. Just like for benzene, it has to be a good leaving group. Okay? Just like this is a good, it has to be a good leaving group. Just like we did for benzene. You can't have an H, it has to be something that's negative, that's good living, so it has to be bromine, iodine, chlorine, halogens are usually the best, okay? Okay, so here, this pyridine has a substituent on C3. Is it the same kind of process? That's the question. We know that you can't have a nucleophilic substitution on just plain pyridine. It has to be substituted. The question is, if my substituent is on C2, what happened? If my substituent on C3, what happened? My substituent on C4, what happened? I'm going to just move this a little bit higher so I can put the three of them. So if it's on, so I'm still going to bring my nucleophile, okay? So here, first step, this adds, the pi bond opens. You understand? You have to open the pi bond. Okay? So we end up with this. And then the second step would be this comes back, this leaves, okay? But it won't happen right now. We have resonance forms, okay? So this can move here, this moves here. Then this moves here, this moves here. And then the last step would be this falls here, the Z leaves, and then you end up with the product. Okay? So it is obvious that the top scenario, the negative charge is where?
On the
On the nitrogen. And in here, no matter what resonance form you write, it's always going to end up on what? Carbon. Which one carries better the negative charge, carbon or nitrogen? Nitrogen, because nitrogen is smaller. So it's obvious that the C2, if you're substituent on C2, that works. If it's on C3, because the negative charge will end on a carbon, which is a larger atom than nitrogen. Now let's see if it's C4, okay? So here's C4. So C4, this comes here, this moves here. I already see that it landed on a carbon. Okay, then what's the next step? This moves here, this moves here. Then then the last step, this falls here, and the Y, the Z leaves, sorry. And you end up with Y. So will this happen?
Yes.
Yes. Why? Because we have a negative charge on the nitrogen. So you can see here for nucleophilic substitution, they will happen on the 2 or the 4. Okay? So if you have a substituent on position 2 or on 4, you will be able to get that. So here's a real example. So for example, if you have, so everybody understands this, as you can see, once you see it done the first time, it becomes easy. So in every nucleophilic substitution, what does it require? First an addition of the nucleophile, then elimination. So I'm just going to give you one example. So it has to be substituted in position 2 and 4. So I'm going to put 2 substituents here just to make it more interesting. So we have 2 substituents. And then the base would be NaNH2. Remember NaNH2, it means Na plus and NH2 minus. So the nucleophile here is NH2 with 2 lone pairs. So which one will be substituted? Why?
Better leaving group.
Better leaving group. Because this is a strong base, but Br minus is almost neutral. OCH3 minus is a strong base also. So it's best to produce the weakest base. So here, you're going to end up with the NH2 attaches here, and the OCH3 stays right there. Because bromine with Na plus is much stabler than OCH3 minus, stronger base. So the reaction always favors the weaker base as a product, from strong to weak, not produce something strong. Okay, one last thing, just like we did reactions on substituted benzenes, we can also have reactions on substituted pyridine. So if I bring this, just want to see how you can kind of think about these things. So if I bring Br2 and light, what does it tell me? Is this reaction going to happen on the ring?
No.
Where is it going to happen?
On the substitution.
Because if it's going to happen on the ring, do we need light here? What do we need? FeBr3 with high temperature. So basically this is just a distraction. You understand? It's just like a substituent. The focus now is on the alkyl. So it's chapter 12. That's radical reaction. So I want you to start looking at the reactions and say, okay, which part am I going to focus on? Which part is just a distraction? So in this case, even though it looks like, oh, there is there pyridine, but the pyridine is just a side thing, just sitting there watching the game, just a spectator, not involved. So here, the product would be CHBr, CH3. And remember, why is it that H and not this one?
Secondary.
Because it is conjugated with the ring, the radical. Another one, like this one. What if I have this, but I use chromic acid? So it's an oxidation. Which part is going to be oxidized? The alkyl group. So you start to see everything we studied with the substituted benzene applies here. Okay? So here, still going to be your pyridine, it's just a spectator. And here we're going to have a COOH. Remember how it chops everything and just leaves one carbon? And that's an oxidation. So these are the side reactions. I just want to put one more thing here. So all of this is related to what? Electrophilic substitution. And we already know that these will go very fast and pyridine will be the lowest. And we already know that these will undergo this. Pyridine will only do no Fidel crafts. We know that this is always C2 or C3, but this is only C3. But what's new here is pyridine compared to benzene. Benzene can undergo what? Nucleophilic substitution, and pyridine can also do nucleophilic substitution. What is the difference is for benzene, you have to have what? You have to have a good leaving group, and you have to have electron withdrawn. For pyridine, we don't need it because the nitrogen itself is what? The electron withdrawn. So all you have to do is have what? A good leaving group. See, when you understand benzene, I need something to withdraw to make it less negative, so I can bring something negative. So for benzene, it's the substituent that withdraws. For pyridine, it's the nitrogen that withdraws. So that's why they are the similar. Okay? But lastly is what position works for substitution for pyridine is different from benzene. Benzene, any position is the same. But for pyridine, it works best at what? C2 and C4. And that's chapter 19, all of it. Yep. Okay, so Wednesday, we'll go back to chapter 10, do some questions from there, and then I'll go back to 18. But we want to go back all the way to chapter 10. So please bring your textbook or an electronic copy of your textbook. We're going to need that.
You mentioned very quickly, I wanted to make sure the test is now on March 4th.
Wednesday. Yeah.